Something was changing around the spacecraft. There was no explosion, no warning light, no dramatic signal announcing that anything had happened, just a gradual transformation in the invisible environment surrounding a machine that had been traveling away from Earth for more than 4 decades. The particles coming from the sun began disappearing. Particles arriving from beyond the solar system became more common. The magnetic field changed. And somewhere ahead of the spacecraft was a boundary that humanity had never directly crossed before. The strange part was that Voyager 2 was not simply leaving the sun behind, it was entering a completely different physical environment, a region where the influence of our star begins to weaken, where material from the sun collides with matter between the stars, and where the familiar bubble surrounding our entire planetary system becomes something far less solid and far more complicated than scientists had imagined. The spacecraft was more than 11 billion miles from Earth, and every measurement it made was telling scientists something about the place where our solar system ends. But there was a problem. Nobody could actually see the boundary. Nobody could photograph it. There was no wall, no line painted across space. The only way to know that Voyager 2 had crossed it was to watch the invisible particles and magnetic fields around the spacecraft change. And when those changes finally arrived, they revealed something unexpected. The edge of the solar system was not a clean frontier. It was turbulent, it was porous, it was compressed. And in some places, particles from our sun appeared to leak across the boundary into interstellar space. This is the real story of Voyager 2's stunning discovery at the edge of the solar system. The story actually begins more than 4 decades earlier. On August 20th, 1977, a spacecraft lifted away from Earth carrying an ambitious collection of scientific instruments, a golden record, and enough determination to travel far beyond the planets humans had previously explored. Its name was Voyager 2. It was built by NASA's Jet Propulsion Laboratory. And at launch, nobody could know just how long this spacecraft would survive. The original mission was not designed primarily to study interstellar space. Voyager 2 was built to explore the outer planets, Jupiter, Saturn, Uranus, Neptune. It would become the only spacecraft ever to fly past Uranus and Neptune at close range. But after Neptune, something extraordinary happened. There was nowhere else to go, so Voyager 2 kept moving. The planets became points behind it, then distant worlds, then almost nothing. The spacecraft continued outward through an enormous region dominated by the sun. Because the sun is not merely a ball of light, it is constantly blowing material into space. A stream of charged particles called the solar wind pours outward from the sun at hundreds of kilometers per second. That wind carries particles and magnetic fields with it, and over billions of kilometers it creates something enormous, a bubble, the heliosphere. It surrounds the planets, it extends far beyond Pluto, and it forms the region of space where the sun's influence dominates the surrounding environment. But the heliosphere cannot expand forever. Eventually, the solar wind encounters the material between the stars. That material is called the interstellar medium. It is extraordinarily thin, but space is so vast that even a tiny amount of matter becomes important when accumulated across enormous distances. The sun is moving through this interstellar environment, so our entire solar system is effectively traveling through an ocean of extremely thin plasma and gas. The heliosphere is the bubble created by that motion and by the outward pressure of the solar wind. But bubbles have boundaries, and scientists wanted to know what happened at ours. For decades, the edge of the heliosphere existed mostly as a theoretical concept. Researchers could model it, they could estimate its position, they could calculate how solar wind should interact with interstellar material, but nobody had sent an instrument directly through it. Then Voyager 1 began approaching the frontier. In December 2004, Voyager 1 crossed a major internal boundary called the termination shock at approximately 94 astronomical units from the Sun. Voyager 2 reached the same region in August 2007 at approximately 84 astronomical units. And that difference immediately told scientists something important. The heliosphere was not perfectly symmetrical. It was being distorted, compressed, pushed, shaped by the surrounding interstellar environment. Voyager 2 then entered the Helios heath. This is the outer region of the heliosphere. The solar wind had already slowed dramatically there. The spacecraft was getting closer to the place where the sun's influence would eventually meet the interstellar medium directly, but nobody knew exactly when that would happen. Then came 2012. Voyager 1 crossed the heliopause. The date was August 25th. It became the first human-made object to enter interstellar space. But there was an important complication. Voyager 1's plasma science instrument had stopped functioning decades earlier, so scientists had to reconstruct the event from other measurements. The cosmic ray data changed, the heliospheric particles dropped, and later plasma wave measurements provided additional evidence that the spacecraft had crossed the boundary. Voyager 2 was different. Its plasma science instrument was still working. That meant scientists had a rare opportunity. They could watch the spacecraft cross the heliopause using an instrument specifically designed to measure the solar wind, and in 2018 the spacecraft began approaching the boundary. The first signs appeared months before the crossing. Cosmic rays from outside the solar system began increasing. In late August 2018, Voyager 2's cosmic ray instruments detected roughly a 5% increase in the rate of cosmic rays compared with earlier measurements. It was interesting, but it was not enough. Scientists knew that similar changes had appeared before Voyager 1 crossed the heliopause. Still, they could not simply assume Voyager 2 was about to cross. The spacecraft was traveling through a different part of the heliosphere. The boundary itself moves. The sun's activity rises and falls over an approximately 11-year cycle, and that changing solar activity can push the heliopause outward or allow it to move inward. So even after more than 40 years of travel, scientists still had to wait. Then came November. November 5, 2018, Voyager 2 was approximately 11 billion miles from Earth, and something changed dramatically. Its plasma science instrument detected a steep decline in the outward flow of solar wind particles. Then the solar wind disappeared from its measurements. Not temporarily. The instrument stopped seeing the familiar outward flow that had dominated the spacecraft's environment for years. At almost the same time, other instruments were detecting an increase in particles originating outside the heliosphere. The spacecraft had crossed. Voyager 2 had entered interstellar space. And unlike Voyager 1, this time scientists had direct plasma measurements confirming the transition. Stay with me here because this is where the story becomes much stranger. You might imagine that crossing the heliopause is like crossing an invisible wall. It is not. There is no sudden empty region beyond it. There is no moment when the sun's influence instantly disappears. Instead, Voyager 2 entered a transitional environment. The boundary was complicated, the plasma outside was different, the density changed, the direction and behavior of the particles changed, and the magnetic field did something that scientists did not expect to be so straightforward. Voyager 2 was showing researchers that the edge of our solar system was not a simple shell. It was a dynamic interaction zone. Think about what that means. For centuries, humans imagined the solar system as a collection of planets orbiting inside an almost empty universe. The planets were the obvious landmarks. The sun was the center. Beyond Neptune was darkness. But Voyager revealed that there is an enormous physical structure extending far beyond the planets. The sun creates a giant protective environment around them, and at its outer edge, that environment interacts directly with the space between stars. The heliosphere is therefore not merely an abstract boundary, it is part of the architecture of our cosmic neighborhood, and Voyager 2 had reached its outer shoreline. But the most interesting discovery was not simply that the boundary existed. Scientists already expected that. The surprise was what the spacecraft found there. One of the first clues came from plasma density. Just before Voyager 2 crossed the heliopause, its instruments detected an increase in plasma density. The material around the spacecraft appeared to be compressed near the inside edge of the heliosphere. That raised a difficult question. What exactly was causing the compression? The solar wind was pushing outward, the interstellar medium was pushing inward, and the two environments were interacting in a way that produced a complicated transition zone. NASA scientists described this region as a perturbed area rather than perfectly undisturbed interstellar space. In other words, Voyager 2 had technically crossed into interstellar space, but it had not immediately entered some pristine, untouched ocean. It was still close enough to the heliosphere to feel its influence. The boundary was not the end of the story, it was the beginning of another one. Then came another discovery. Particles were leaking through. One of Voyager 2's particle instruments detected evidence that some particles originating inside the heliosphere were making their way across the boundary and into interstellar space. The heliosphere was not completely sealed, it was porous. That single observation changed the mental picture. If the heliosphere were an ideal bubble, scientists might expect a sharp separation between the solar material inside and interstellar material outside. But nature does not always produce ideal boundaries. The edge was more like an interface. Particles could cross, fields could interact, plasma could compress, and the two environments could influence one another. This was one of the most important lessons from Voyager 2. The boundary separating our solar neighborhood from interstellar space was not a rigid border. It was an active physical system. And then there was the magnetic field. This may be the most subtle part of the entire discovery. Voyager 2's magnetic field instrument measured the magnetic field immediately beyond the heliopause. Scientists found that the direction of the magnetic field in that region was remarkably aligned with the magnetic field inside the heliosphere. That was surprising, because outside the heliosphere, the spacecraft was supposed to be sampling the interstellar magnetic environment. Yet the magnetic geometry did not simply flip at the boundary. Instead, the fields appeared to remain aligned across the transition. Voyager 1 had seen a similar phenomenon. Voyager 2 independently confirmed it. And suddenly the boundary looked less like two completely separate worlds and more like two environments physically connected by a complicated interface. This matters because magnetic fields control the motion of charged particles, and almost everything Voyager is measuring out there involves charged particles. The solar wind is plasma, the interstellar medium contains plasma, cosmic rays are charged particles. Magnetic fields guide their trajectories, so when the magnetic field changes, the particles change. When the particles change, the energy balance changes, and when all of those things interact, interact, the heliosphere becomes a giant natural laboratory, one that Earth cannot reproduce, one that no experiment on our planet can fully simulate, and Voyager 2 is sitting inside it, a machine built in the 1970s, operating billions of miles away, sending measurements home across a distance so large that a radio signal takes more than 18 hours to travel from Earth to the spacecraft and back. That delay creates another extraordinary part of the mission. When engineers send a command, they cannot watch the spacecraft respond immediately. The signal must cross the enormous distance. Voyager 2 receives it, then the response travels back. Every adjustment is slow, every problem is dangerous, and every scientific measurement is precious. In 2018, that patience paid off, because Voyager 2 was carrying something Voyager 1 did not: a working plasma science instrument. The instrument could directly measure the properties of the surrounding plasma. It could tell scientists about the flow, density, temperature, pressure, and behavior of the solar wind. That made the crossing much more informative. For the first time, researchers could observe the transition from the solar environment to interstellar space with multiple instruments working together. The cosmic ray detectors showed the changing particle population. The magnetic field instrument tracked the field. The plasma instruments detected the changing environment, and together they created a picture of the heliopause that no single instrument could provide. This is where the title of the story becomes important. Voyager 2 did not discover aliens. It did not detect an artificial transmission. It did not find a mysterious object hiding beyond the planets. Its discovery was more profound than that. It discovered that the edge of our own cosmic environment was much more complicated than the simplified picture scientists had been carrying in their heads. The sun does not simply stop influencing space at one clean line. Its influence fades, collides, compresses, leaks, and interacts, and the surrounding galaxy pushes back. The heliosphere is constantly negotiating with interstellar space. That negotiation changes with solar activity, it changes with the spacecraft's position, it changes with the surrounding magnetic field, and it may even affect how radiation reaches the planets inside. This brings us to one of the most important reasons scientists care about the heliosphere. It is not only a boundary, it is also a shield. The heliosphere helps reduce the number of high-energy cosmic rays that reach the inner solar system. Voyager measurements showed dramatic changes in particle populations as the spacecraft crossed the heliopause. Inside, particles originating from the sun were more dominant. Outside, cosmic rays from beyond the heliosphere became much more prominent. That transition is a reminder that Earth exists inside a protective cosmic environment. We rarely notice it because we live deep inside the bubble, but Voyager has traveled far enough to experience what happens when that protection becomes weaker, and that creates a much larger question. How important is the heliosphere to life on Earth? Scientists already know that the sun's activity changes the size and structure of the heliosphere, but stars are not all equally quiet. Some are far more active. Some produce enormous stellar eruptions. Some may generate very different protective bubbles. So if a planet orbits another star, its exposure to interstellar radiation could depend partly on the size and strength of its star's astrosphere. The heliosphere is therefore not merely a curiosity, it may be part of the broader question of habitability across the galaxy. But Voyager 2 was not finished. After crossing the heliopause, it continued deeper into interstellar space. And this is where the mission becomes almost surreal. The spacecraft was launched in 1977. A generation passed, then another. Humans changed. Technology transformed. The internet appeared. Mobile phones became ordinary. Entire industries were created and disappeared. Yet Voyager 2 continued sending data. A machine built before the first space shuttle flight was still communicating with Earth from beyond the heliosphere. The spacecraft had become something more than a probe. It had become a moving historical record. But history was not what its instruments were measuring. They were measuring the environment between the stars. And that environment is not completely empty. Interstellar space contains plasma, it contains magnetic fields, it contains cosmic rays, it contains atoms and dust, it contains the remnants and products of stars that existed long before our sun was born. Voyager 2 was sampling that environment directly. For the first time in human history, we had instruments operating outside the sun's protective bubble. Only 2 spacecraft have achieved that. Voyager 1 and Voyager 2. That makes their measurements uniquely valuable, but it also means there is a clock running. Voyager spacecraft are powered by radioisotope thermoelectric generators. The electrical power slowly decreases with time. The spacecraft cannot run every instrument forever. Engineers have to decide what science is most valuable. In 2024, NASA shut down Voyager 2's plasma science instrument to conserve power. That decision was not a failure, it was the opposite. The instrument had already achieved one of the most important objectives of the entire mission. It helped confirm Voyager 2's entry into interstellar space in 2018. Now engineers were trying to preserve enough energy for the spacecraft to continue making measurements with its remaining instruments into the 2030s. Think about that. A spacecraft launched in 1977 is now operating in an environment that no human being has physically visited, and the mission team is still making decisions about which measurements deserve the remaining watts of electricity. Every watt matters. Every command matters. Every bit of return data matters. Because eventually the signal will become too weak, the instruments will stop, the transmitter will fall silent, and Voyager 2 will continue moving. It will not stop when we stop hearing it. It will simply become another human artifact traveling through the galaxy. But before that happens, there is still science to do. And one of the biggest questions concerns the shape of the heliosphere itself. For a long time, scientists pictured something roughly bubble-like around the Sun. But Voyager observations have shown that it is not a perfect sphere. The heliosphere can be compressed. Its shape is affected by solar activity. It interacts with the interstellar magnetic field. Voyager 2 crossed the termination shock at a substantially different distance from Voyager 1, and the two spacecraft encountered the heliopause at different locations. Those differences tell scientists that the heliosphere has structure. It may have a distorted shape influenced by the Sun's motion through interstellar space and by the magnetic field of the surrounding medium. NASA has compared the heliosphere to a ship moving through an ocean. The analogy is useful because the solar system is not stationary. The Sun is traveling, the heliosphere travels with it, and the interstellar medium flows around it. The result is an enormous cosmic interaction zone. Now imagine zooming out. Earth is orbiting the Sun is moving through the Milky Way, the planets are carried along inside the heliosphere, and the heliosphere itself is moving through interstellar space. So even while you are sitting completely still on Earth, you are traveling through multiple layers of motion. Your planet moves around its star, your star moves through the galaxy, and the galaxy itself moves through the larger universe. Voyager 2 is simply the first machine we built that has traveled far enough to sample the environment outside our star's protective bubble. That perspective is difficult to appreciate. The spacecraft is not just far away, it is beyond the region where the solar wind dominates. It is in a place where the Sun is no longer the only major player. The galaxy is becoming part of the measurement, and that is where another important distinction becomes necessary. Voyager 2 has entered interstellar space, but it has not truly left the solar system in the gravitational sense. That sounds contradictory. It is not. The heliopause marks the boundary of the heliosphere, but the Sun's gravitational influence extends much farther, far beyond the planets, far beyond Pluto, out toward the distant Oort cloud, where countless icy bodies may orbit the Sun at enormous distances. So when we say Voyager 2 entered interstellar space, we are talking about the region beyond the heliosphere. The solar system itself extends much farther. This is another reason the phrase edge of the solar system can be misleading. We are dealing with several different definitions of an edge: the edge of the planets, the edge of the solar wind, the edge of the heliosphere, and eventually the outer limit of objects gravitationally bound to the Sun. Voyager has crossed one of those boundaries, not all of them, and that distinction becomes important when we imagine where the spacecraft is actually going. It is not approaching another star anytime soon. It is moving outward into the galaxy. Its trajectory will carry it through interstellar space for an almost incomprehensible length of time. Eventually, long after its instruments have stopped working, Voyager 2 will continue on. The spacecraft will become silent, but its trajectory will remain. A small machine drifting through the Milky Way, carrying a record containing information about the civilization that built it. And perhaps the most remarkable thing is that the spacecraft was never designed with this final chapter in mind. Nobody in 1977 could have known exactly what it would discover. The scientists who planned the planetary mission were focused on Jupiter, Saturn, Uranus, and Neptune. The interstellar mission came later. The spacecraft survived long enough to become something much bigger than its original purpose. That is why the Voyager story is not simply a story about distance, it is a story about persistence. A machine designed for years lasted for decades. A mission designed around planets became a mission between stars. And an invisible boundary that existed mostly in equations became a place that human instruments could actually sample. But there is still a deeper mystery. If Voyager 2 has crossed the heliopause, what exactly happens to the Sun's influence after that? Does the solar magnetic field simply fade away, or does it continue to shape interstellar space much farther than we can currently measure? How far does the Sun's particle environment extend? How quickly do solar particles mix with the interstellar medium? And how does that interaction change as the Sun moves through different regions of the galaxy? Voyager can answer some of these questions, but not all of them, and that is what makes the mission so valuable. It is not closing the mystery, it is expanding it. Before Voyager, the outer boundary of the heliosphere was largely theoretical. After Voyager 1 and Voyager 2, we know the boundary exists. We know it is dynamic, we know it is asymmetric, we know particles can cross it, we know magnetic fields can remain surprisingly aligned across it. We know the plasma environment changes dramatically. And we know that interstellar space is not simply an empty void beyond the planets. It is a physical environment, a place with structure, a place with pressure, a place with magnetic fields, a place filled with particles moving through a galaxy that is itself constantly changing. And Voyager 2 is giving us a direct sample. There is something almost poetic about the fact that the spacecraft discovering this frontier is itself ancient. Its computer is primitive by modern standards. Its power supply is weakening. Its radio signal is extraordinarily faint. And yet, it is exploring a region no modern telescope can simply photograph. Because some frontiers cannot be seen from a distance, they have to be crossed. That is what Voyager did. It crossed. And when it did, it found that the boundary was not where the story ended. It was where another story began. In 2018, the spacecraft crossed the heliopause. In the years afterward, its instruments continued studying the environment beyond it. In 2024, engineers began shutting down instruments to preserve the remaining power. The spacecraft kept going, and every year that it survives adds another piece to a scientific record that may never be duplicated in exactly the same way. Because Voyager 2 is traveling through a region that changes with the sun, a future spacecraft following the same general route would not necessarily encounter the same conditions. The heliosphere expands and contracts. Solar activity changes, the interstellar environment changes, the spacecraft's position changes, the galaxy is never perfectly still. So Voyager's measurements are not just photographs of a location, they are observations of a moment in the life of our star. And that may be the most important discovery of all. The sun is not isolated, our solar system is not an island, the space between stars is not empty.